All right, so I have literally stepped out of a meeting, department meeting, and it was concerning the lab kits. We are still coming to consensus, but I had to take off 10:30. Meeting's going to go to 11. So those of you who have not received a lab kit, Carolina Biological has once again promised us that they are actually shipping out today, and they should be to you within at least the next 2 business days, which puts them, if not this weekend, midweek. You will receive an email from me with information updating the lab kits as soon as I hear back from this meeting. Again, it wasn't done when I was left. We basically had just gotten the update saying, hey, this is what Carolina Biological has told us and promised us, and we were supposed to decide from there what to do. But those of you who have not gotten the lab kits yet, yes, we share your frustration. We agree Carolina Biological was not honest with us about their ability to fulfill these orders, and we're trying to figure out what to do to kind of like mitigate this situation. But again, you're going to receive information from me as soon as we get information. Now, I want to go ahead and start off this live stream talking about Hess's Law. And Hess's Law is one of those that typically what a lot of instructors have taught in Chem 1 is adding and subtracting reactions. This can be done. Here's two major issues. First of all, no one does this in practice. And what you're going to learn, what I'm going to teach you is much more is what is actually done. The second is that the adding and subtracting reactions is a horribly impractical thing. Unless you have the reactions that you know you can add and subtract, you can't really answer any questions. So, how does Hess's Law work? Well, Hess's Law is very much an accounting thing. What it does is it treats each molecule as if it contains its own enthalpy and its own Gibbs free energy. Now, the energy we're going to reference here is the heat of formation, or enthalpy and the Gibbs free energy of formation. So there's a delta HF naught. This naught refers to the formation energy at room temperature in 1 atmosphere. And the reason we use this definition is that for any diatomic gas, O2, C2, O2, N2, I2, Cl2, Br2, H2, any diatomic gas, the heat of formation is 0. Also for any element at room temperature, so in this case carbon, that's going to have a heat of formation of 0. Now, a common misconception students have is that if it's just an element by itself, it's automatically 0. That isn't true. When we defined the reference temperature and pressure, we said, what does that element appear like at that temperature? So if we have oxygen, I just say oxygen, you should automatically think O2, because that's what's in air. So something like O3, ozone, that doesn't naturally exist. We have to supply heat. So the delta H is non-zero. Monatomic oxygen, O does not have a delta H formation of 0 because oxygen exists as O2. We had to apply heat or remove heat to split the atoms apart. So again, it's diatomics and every other element on the periodic table, not the diatomics by itself. Now, big picture, what Hess Law says is that if we look at any reaction, the delta H of that reaction is just the enthalpy of the products minus the enthalpy of the reactants. It's just an accounting. The energy that is gained or lost is the difference in the energy between the products and the reactants. So I'm not going to use delta HF in all of these. I'm going to just use H. This is just a shorthand that I like to use because writing the delta HF not multiple times makes it very hard to see. So to use Hess's Law to solve these types of problems, what you do is you just start by writing out the Hess's Law expression for each reaction. So for this top reaction, and you can find this in the packets on page 26. So page 26 in the packets, enthalpy without tables. This is the top problem. We have 2 molecules of H2O and 2 molecules of CO2. So that's how much we finish with. Hess's Law, products minus reactants. So if we start with that much, what did we start with? Well, we start with however much enthalpy C2H4 has and however much enthalpy 3 O2 molecules has. And we know from the experiment this has an enthalpy change of minus 1,323 kilojoules per mole. So for each reaction, we're going to go through this process. It's always products minus reaction, and it's the enthalpy, the delta HF of formation of each of these molecules. Going to add them up for products, add them all up for reactants, take the difference, and this is going to get us to the delta H of the reaction. For this one here, the delta H is twice the enthalpy of H2O. So there's our products, minus twice the enthalpy of H2, plus the enthalpy of O2 equals minus 483.6. Delta H here is the enthalpy of CO2 minus the enthalpy of carbon plus the enthalpy of O2, which equals minus 393.5. And for the last reaction, which is the one we want to solve, the delta H is the enthalpy of C2H4 minus twice the enthalpy of carbon plus twice the enthalpy of H2. So that's your first step. Just write out the Hess Law expression for each reaction. The next step, you need to cancel out everything that is zero. So again, any diatomic gas, H2, N2, O2, I2, F2, Cl2, Br2, I2, they're all going to disappear because fundamentally what's happening is it doesn't take any, you don't gain or lose heat making oxygen from oxygen at room temperature. To make O2, you've already got it, so there's no heat gained or lost. The diatomics immediately disappear. Next, if we see any pure elements by themselves, so in this case we've got carbon, but if we had something like calcium, sulfur, lithium, any element by itself is going to have zero because it hasn't made or broken bonds. So to make lithium from lithium at room temperature doesn't take any heat. So we have the enthalpy of carbon is zero, carbon is zero. Now we're just going to erase the terms and see what remains. So when I finish, I'm going to get algebraic relationships. So you get twice the enthalpy of H2O, which is going to be non-zero because these aren't pure elements and these aren't diatomics, minus twice the enthalpy of CO2 minus the enthalpy of C2H4 equals minus 1,323. Twice the enthalpy of H2O equals minus 483.6. And the enthalpy of CO2 is minus 393.5. So I've got this piece of information here. The heat of formation equals minus 393.5. From this relationship, I can divide by 2, and I get that the heat of formation of H2O is minus 241.8 kilojoules per mole. Now, with this information, this is going to be true regardless of anything else. So once we know the heat of formation of a molecule, it's always going to be that heat of formation. So up here, I've got twice the heat of formation, CO2, of H2O. So I get that number from there. Plus twice the heat of formation, CO2, which I get from there. Minus the heat of formation of C2H4, which I don't know, equals minus 1323. So, in order to find out the heat of formation of C2H3, all I have to do is move this over, move this number over. So if I just do some algebra, and I can solve now for the heat of formation of C2H4. The final answer here works out to be that it's just whatever the heat of formation of C2H4 is. So this is how you do it by using Hess's law. For each reaction, you're just going to write out the Hess's law expression for each reaction, cancel out any zero terms, and then you're just using algebra to solve everything else. I would really recommend you solve it algebraically. You're going to quickly find the numbers get kind of daunting. The biggest mistake I see students do is that sometimes they'll subtract a negative. When you subtract a negative, you forget that you're subtracting a negative, which is actually just adding it, not subtracting it. But again, this is where showing your work is going to come in really handy. Now, how does this change if you go to Gibbs? Well, the only thing that changes is that it goes from H to G. So instead of working with the heat of formation, we work with the Gibbs of formation. So once you've solved this problem once, and then you switch to Gibbs, with Gibbs you're just changing numbers, but the approach stays the same. Now, student did ask yesterday in the live stream, is it possible to still add these with adding and subtracting reactions? You can. I don't advocate it, but it will definitely be an option available to you on the exam. So how do you approach those types of problems? Well, they're a little bit trickier, but they can be done. And the reason I don't like this method, other than the fact it's not done in practice, is that it requires a degree of cleverness. So how do you do it? Well, the way I teach it is that, first of all, you need to figure out if there's a positive or negative sign on these equations. And to do that, we look at the final reaction compared to the first reaction. So the bottom reaction here has the C2H4 as a product. Up here it says it's a reactant. So odds are we're going to subtract this reaction. Subtracting it has the effect of reversing it. If we look down here, we've got H2, and so the H2 is on the left here, the H2 is on the left here. We're probably going to add this reaction, and here we got carbon and carbon, so odds are we're going to add this reaction. The next step is you have to figure out what you're going to multiply each reaction by. And so you're going to look at each of the reactants and see what the coefficients are. There's a 2 here, there's a 1 here, so we need to multiply this whole reaction by 2. Give us 2C, 2O2, 2CO2. H2, we've got a 2 here and a 2 here, we're going to multiply by 1. We've got a C2H4 here, we've got a C2H4 here, you're going to finish with a 1. The challenge is sometimes you can get fractions, and you're going to know you're going to get a fraction when you have like 1 here and there's like a 2 up here. In this case, you would multiply by half. The other complication is that if you have a molecule that appears in multiple reactions, so there's some examples where you see where like hydrogen and oxygen is in multiple ones, you're not going to be able to figure out what to multiply by until you kind of work everything else out, and then you're probably going to have 1 or 2 reactions that, like, they're kind of there to balance out the oxygen, the hydrogen, whatever's in there. Now, another thing to keep in mind, you can get a coefficient of 0 as well. So because these are set to be solved both by Hess's law as well as by adding and subtracting, if you don't use a reaction, you're just multiplying the whole thing by 0. Now, before you get done with doing this whole process, make sure it works out. So if we subtract this reaction, add this reaction, do twice this reaction, we've got 1, 2, 3 O2s. So our 3 oxygens cancel out. We've got 2 CO2, 2 CO2. So our CO2s will cancel out. 2 H2O, 2 H2O. So our 2 H2Os will cancel out. And we get our 2C, our 2H2, and our C2H4. So this works out. Now, how does that get you your final delta H reaction, or delta G? Well, I've written delta H1, delta H2, delta H3. All we're going to do is take this coefficient and multiply it by this number. So we get minus delta H1 plus delta H2 plus twice delta H3. And when you do that algebra, you'll recover the delta H of that reaction. Gibbs is going to be the same way. Once you know how to add and subtract these reactions to get the final reaction, you're going to do the exact same things to the delta H, the delta G's to get the Gibbs free energies. Now, on the last page of the packets, and again, you need to be able to do that whole back end of the packets. I don't have web assignments for it because they're incredibly hard to program, and they're incredibly hard for students to work on because there's so many intermediate steps. It asks you about finding the delta S. We have the relationship delta G equals delta H minus T delta S, and this is the Gibbs relationship. If we know delta G for the reaction and we know delta H, and if you look at the package, you'll see that there's 6 reactions for delta H, 6 reactions for delta G, and they're the same reactions, just delta H, delta G. Once you know these numbers, and it gives you the temperature, then you can solve for the delta S. Now, that was one of the questions I was asked today. Another question I was asked, and then I'll get to the live stream questions. The EA discussion board question. I'm not seeing an EA discussion board question. not seeing one. I guess just conceptually I'll go over how to solve for EA. So typically what we measure experimentally is K versus T. So we get temperature with a bunch of numbers and our rate constant K with a bunch of numbers. Now, transition state theory says that K should equal some pre-exponential factor e to the minus EA over RT. And if we take the natural log of both sides and rearrange, we get the natural log of K equals minus EA over R times 1 over T plus the ln of A. So if we plot the ln K as Y and 1 over T as X, we should get a straight line. Y equals mx plus b, where n here is minus EA over R, and b here equals the ln of A. If we rearrange EA, it's just minus R times the slope, and the pre-exponential factor is just e to the y-intercept. But that's not the data we're given. We're not given ln of K and 1 over temperature, so we have to convert. And to do this conversion, we're going to take our temperature and we're going to get 1 over temperature, typically because we don't report the lab, plus 273. Now, if you do the 273.15, you still need to obey the rules of sig figs. If you don't have that 0.00 precision, then you need to leave it as just 273. In fact, for all these problems, just stick to 273, not the 273.15. You don't have that degree of precision on these numbers. For the K, we're going to transform the K to the ln of K. So this is going to become our X. This is going to become our Y. We will generate the plots, fit the plot with a straight line, and use the parallels here to find the pre-exponentials in the EA. So now I can get to the live stream questions. Can you work out concentrations from KAQ homework question 2? As soon as I can get it up. Alright, so I'm going to share the desktop with you while I write this problem up on the board. So what is the concentration of H plus if a solution has a starting concentration of 0.1 molar H2C2O4, 0.025 molar NaHC2O4, and the Ka here is 0.0590. So let me get that written up on the board really quick. And it is telling you 3 significant figures. And there's we'll talk about why it's giving you, why it's specifying the 6 figures for you. So for any equilibrium problem, we need 3 things. We need, first of all, we need the expression for Q. We need KQ equals Q, and we need an IC table. Now the reaction is given to you. H2C2O4 goes back and forth to H plus HC2O4 minus 1. The potassium here is just a spectator ion. It's there to solubilize the HC2O4. This is kind of a Chem 1 concept where we talk about spectator ions when balancing net ionic equations. So this problem is giving you the concentration of H2C2O4 and the concentration of HC2O4 minus 1 on those, based on those numbers. Now, the 3 things we need KQ equals Q. So our KQ, Ka is just a special case of KQ. It equals Q. So what does Q equal? Well, you're going to need to watch the online videos or read the notes. There is a lot that goes into how Q is proven, but the short answer is that it's the concentration of the products raised to their coefficients divided by the concentration of the reactants raised to their reaction coefficients, with the concentrations of solids and liquids written out as 1. So in this case, everything is AQ. So Q is the concentration of HC2O4 minus 1 and H plus all over H2C2O4. Now, this is the equilibrium concentration. So if we are looking for an equilibrium concentration, every concentration here is at equilibrium. Now, the third thing we need is an IC table. Now, you may have been exposed to ice boxes or ice tables in Chem 1 depending on who you have. So let's take a quick crash course in how you set those up and why they are what they are. So for an ice table from Chem 1, we'll talk about why I'm also doing the last E in red. Typically with Chem 1, you've only got the 3 rows, I, C, E. I is initial. C is change. E is end, or in this case, equilibrium. And the red E here is also going to be equilibrium, but we're going to talk about why this is a special row. Across the top, you've got columns corresponding to the concentrations of your reactants and products. Now, I always keep the reactants on the left and the products on the right. We'll talk about why in just a minute. So my reactant here is H2C2O4. Products are H plus and HC2O4 minus 1. First thing I ask you for is the initial concentration. So the initial concentration of H2CO4 is 0.1 molar. You're not given H plus, so you're just going to assume it's 0. H2CO4 you're given is 0.0250. Now, the change row. There are two schools of thought on how to do the change row. One school of thought is that you need to figure out if the reaction goes forward or backwards. And under that definition, it will set the signs on the change. The way I was taught to do it and the way I would advocate for you to do it is that the change is always negative for reactants and positive for products. And we'll talk about just a minute why this can create problems for you. But the question is whether or not you want to do a lot of work up front or you want to do all the work on the end. For ice tables and equilibriums, I really recommend you do all the work at the end. Now, what is the actual change? Well, it's an equilibrium reaction. There's no such thing as a limiting reagent because we never go to completion. So our change here for each row is the reaction coefficient times X. So this is our reaction coefficient, and X here is the extent of reaction. So H2C2O4, the reaction coefficient is 1, so it's 1 times X. For H plus, it's 1 times X, and for HC2O4, it's 1 times X. The E row is just the I row plus the C row. So this is 0.1 minus X, this is X, and this is 0.0250 plus X. So what's the bottom E row? Well, two things. One, these are numbers. This is algebraic. So your blue E row here is the algebraic expression for the equilibrium concentration. The red row is the number. Now, sometimes we are given equilibrium concentrations and asked to solve for other things. So we can be asked to solve for KQ, we can be asked to solve for other concentrations. The point is, the blue E row equals the red E row. So if we have a number, it's going to equal this algebraic expression and vice versa. This algebraic expression is going to equal this number. The problem is asking you for the equilibrium concentration. So you got your ice table, you got your KQ equals Q, and you got your expression for Q. What the problem is asking you for is the equilibrium concentration of H plus, which is this square. So ultimately we need to solve this square, and we know that this square here, the red square, equals X. So if we can find X, we can find the equilibrium concentration of H plus. Now, IC tables. You can put either one of these rows into this expression for Q. So since we don't know these, we're going to put the blue E row in. And what we'll get is that H plus is equal to X. Concentration of HC2O4 is 0.025 plus X. And the equilibrium concentration of H2C2O4 is 0.1 minus X. So this all equals Ka, which is 0.0590. So from here, it's just algebra. You're going to use the quadratic formula to solve for X. Now, a common mistake students make on these types of problems is they solve for X and they say they're done. A few things with this. First of all, in this case, X equals our equilibrium concentration, but if I ask you for the equilibrium concentration of HC2O4 minus 1, this square here, it's actually 0.0250 plus X. If I asked you for the concentration of H2C2O4, it's actually 0.1 minus X. So getting X does not mean you've solved the problem. It means that you found the extent of the reaction. You have to further translate the extent of the reaction into the final concentrations. Now, another thing students kind of struggle with on these, they assume that the positive X root is the correct root. And there's an issue with that. If you do the work up front, meaning that you determine if the reaction goes forward or backwards, and there is a way to do that, you would be correct. The positive root is always the solution. Here's the thing. That's a lot, in my opinion, that's way too much work to do up front. You've got a quadratic equation. You're going to get two roots. In this case, a positive X and a negative X. How do you determine which one works? So this mindset of it's always positive is kind of like skipping over details. We need a solution where when we use the extent of reaction, we don't end up with a negative concentration. So what we're going to do is we're going to look at our two roots. We're going to get a positive root and a negative root, and we're going to plug in the root values down here to see if we end up with a negative concentration. One root will give us a negative concentration, one root will give us a positive concentration. That's the one we go with. Now, we happen to have a situation where our concentration equals X, so that means that the positive root has to be the right answer. But let's say you have something like 0.1 plus X here. Well, the negative root may not necessarily give you a negative concentration. So if your root is like 0.05, this will work and this will work, but your positive root may make this go negative. So what does that mean? Well, actually there's a good physical interpretation behind it. If X is greater than 0, the reaction went forward. If X is less than 0, the reaction went backwards. So, if we have a reversible reaction and we have too many products, we can get a negative extended reaction. That's fine. It just means the reaction went backwards. If we get a positive extended reaction, it means that we didn't have enough products, so we went forward. That's all that means. So, but again, it depends on your framework. What I prefer to do, what I prefer students to do, and how I teach it, is that we make this definition. The change is negative for reactants and positive for products, and we decide at the end which way the reaction goes. If our negative root is the one that gives us nothing, is the one that gives us positive concentrations, it just means the reaction ran in reverse to get back to equilibrium. If the positive root works, it means that the reaction had to go forward to get to equilibrium. We can get positive and negative roots. So if anyone says extended reactions can't be negative, that's not really true. Extended reaction can be negative, it just means the reaction went backwards. If you take the time up front to determine if the reaction goes forward or backwards, then you define the changes differently. So if you find that the reaction needs to go backwards, you would actually say the change for the reactants are positive and the change for the products are negative. Some people teach that. I just think it's a lot of work when you can just kind of dump all the analysis at the end, and it forces you to understand what makes the roots work. A valid root, a valid solution for X is one where all concentrations are greater than 0. You can't have a negative concentration. But this is effectively how you solve all the problems on the equilibrium homeworks. Set up your expression for KQ through Q, equate Q to KQ, build your IC table, and then depending on what you're being asked to solve for, that's what you're going to go for. In this case, it wanted an equilibrium concentration, and the only way to get at that was to solve for x. Sometimes you're going to be given an equilibrium concentration, so you're going to be given a number down here. You can connect that to x, and then use that to get to the other values around it. But yeah, that's how you do question number 2. When you solve this one, you're going to get 0.0455 or 0.0456. A fair bit of warning. The homeworks are meant to mostly be doable with a calculator. You are going to find, particularly when that KQ starts getting to be less than 10 to the negative 3, 10 to the negative 4, the TI-34s, the little handheld calculators, those begin to struggle with those types of problems because they don't carry enough precision. Something like a TI-83 or equivalent should be able to handle those. If you want to use PolySolve, go for it. I'm not testing you on your ability to use the quadratic equation. But so if your calculator can do PolySolve, use PolySolve. Otherwise, you're going to have to solve the quadratic equation. That said, I give you the quadratic equation, and you can just look it up. But that's more the harder part with these types of problems. For all of these problems, this is the approach. For all equilibrium problems, this is how you need to start the approach, and then figure out, identify the variable that you're solving for. Now, I'll also give you fair warning, this test 3 is your hardest test simply because this is a very conceptual test. You're going to find with the test, you can do hundreds of problems. These are all going to be different flavors. So there are lots of ways to present this concept and test on it. You're going to find, even within the packets and within the homeworks, it's hard to find 2 examples that are exactly the same. So very much focus on understanding the concepts. Again, take this approach. So you have to have an IC table to solve these problems. You have to have your expression for Q to solve these problems. You have to have the reaction. If you don't have any of those things, if you're trying to solve an equilibrium problem without an IC table, you are doing it wrong. There is no way around it. So use the IC tables. I have videos on how to use IC tables. I think I even have a video on how to work through an equilibrium problem. Go to those resources. But again, if you're trying to solve these homework problems on equilibrium without using an IC table, you're not doing them correctly. Other questions? There's an X on top. So let's do this somewhat algebraic. You get Ka equals 0.0250 plus X times X all over 0.1 minus X. So if I bring this over, I get Ka times 0.1 minus X. And if I factor out, I get 0.1 Ka minus X times Ka equals, I'm going to factor that out, 0.025x plus x squared. Ideally, you're going to bring everything over to one side. I prefer just to keep x squared term positive for ease in the quadratic equation. So I get 0. I've got x squared plus 0.025x plus x times Ka minus 0.1 times Ka. If I group the like terms, I get 0, x squared plus 0.025 plus Ka, x minus 0.1 times Ka. From here, you have to use the quadratic equation. The quadratic equation says that any equation of the form of this form, x equals the opposite of b plus or minus the square root b squared minus 4ac all over 2a. In this case, a is 1, b is 0.025 plus ka, and c in this case is minus 0.1 times ka. So when you solve this, you're going to end up with a positive and a negative root. Again, we know the positive root works not because the positive root is always the correct answer. It's because our extended reaction x equals the concentration of H plus. So this puts the stipulation on that x has to be greater than 0. Otherwise, we get a negative concentration for H plus. Yeah, when you work that out, you should get 0.0455. You're welcome. A lot of this becomes exercises in algebra, particularly if you look on the packets. They're what are called very hard equilibrium problems. So starting on page 16, I would never give you a problem that's insanely hard. And so page 16, 17, 18, 19, those are incredibly hard questions that I would never give you on an exam practically. But the reason for giving you those questions is to show you that you can set them up. And once you get them set up, you realize what makes them hard is that they are just ridiculous amounts of algebra. But the concept is the same. You would solve them the exact same way you would solve the easy equilibrium problems. It's just in this case, you've got like quadratics sitting on top of quadratics, so there's a lot of rearranging that goes on. Particularly on exam, getting to this point where you've got the correct expressions and you're getting down to the quadratic, this is pretty much 80% of the credit right here. Getting the correct roots and being judicious on which root you use, that's going to be another 10%. So making sure that you pick a reasonable root, and also do you understand what's considered a reasonable root. Biggest issue I see at this point is just people put it into the calculator wrong. Again, that's why 80% is up to here. If you got to this point, you clearly understand how to solve the problem. The odds are this is probably just calculator input error. If you had more time, you weren't sitting and taking an exam, you could probably get it correct. But again, getting to this point is conceptually the more challenging part. This is just exercises in algebra. This is where we also see how like poorly your math courses have prepared you for practical math. Other questions? Again, just a reminder for all of you who haven't done the exam, it is due tomorrow practically by 10:50, or yeah, 10:50 because you got, or 10:45. Try not to wait that late to do it. I will try to have the exams graded by Monday morning. So you just got a question. Can you work out number 3 of the free energy changes in Q? These are very much, so these types of problems are very much on the super easy end of the spectrum. Now, common mistakes students make with these types of questions. It is not asking you to find the equilibrium concentration. It is simply asking you what is delta G naught and what is Q under these conditions. So if you're being asked to find the delta G at these conditions, what you're being asked to find is the real free energy change. So let me write this up really quick. 0.321. Oh, good lord. C6H7OH 2 72 0.321, not 321, 026 236 molar. In C6H7O7H in 0.0126 molar H plus, and your reference delta G is 17.8 kilojoules per mole, and the temperature here is 75 degrees C. So again, if you're being asked to find the free energy change, you are not being, read the question, it is not asking you to find the equilibrium values. At equilibrium, so at EQ, the delta G is 0. The delta G naught is pretty much never 0. So what's the distinction? The delta G naught is the free energy change assuming 1 molar of all the different reactants and products. So at 1 molar, this is the delta G0. So the question is, what's the actual delta G? Well, we have the reference, which is the 1 molar, and then we have RT ln of Q. So what this is saying is that to find the real free energy change, the actual free energy from going from reactants to products at this given temperature and concentration, we just tack on a correction term. So Q here, based on the reaction, is the concentration of H plus. That's why you're feeling so loose. Concentration of C6H7O7 H negative. All over the concentration of C6H7O7 H2. You're given all 3 of these numbers. So you're given the H plus 0.0126. The concentration of C6H7O7H is 0.0236. And the concentration of the parent acid is 0.321. So you would just put those numbers in there and get a value out. In this case, it works out to be 9.26 times 10 to the minus 4. To solve for the delta G, plug in your value of Q. Your R here is going to be 0.008314. Your temperature, because you got the gas constant R, is going to be that in Kelvin, so that's going to be 348 plus 273. Yep, 348 Kelvin. Don't do the 0.15, you don't have that precision on this number. And the delta G naught here is 17.8. So these are very much more plug and chug kind of problems. It's asking you to find the free energy change. It is not asking you to find the equilibrium concentrations. Now, there is a consequence of this equation. So I'm just going to erase this part, write it back out. So at equilibrium, delta G is 0, and KEQ equals Q. So if only at equilibrium, so if and only if we are at equilibrium, can we make this claim that KEQ equals Q. Now, at equilibrium, the delta G is 0. What this means is that it's not favorable, more favorable to be a reactant or product, which is what you expect at equilibrium. The reactions going back and forth between reactants and products. A delta G is 0 means that it's not favoring one direction over the other. So we get 0 equals delta G naught plus RT ln of KEQ, because Q equals KQ. And if we rearrange, we get minus RT ln KQ equals delta G0. And so that's where this relationship comes from. Now, I just gotten, for some odd reason, my internet went out for like a brief second there. So let me know if there's any part of that you missed, because it looks like it kind of cut off the last little bit where I said delta G naught equals minus RT ln KQ. Yeah, you're welcome. Other questions? All right, give it a few more minutes and then we'll head out. All right. Since I'm not seeing any other questions, thanks to all of you who were able to show up today. Again, if you're watching these live streams, feel free to email me your questions in advance. I will try to work out the emailed questions first, just so you don't have to sit through too much of the live streams to get your questions answered. Don't forget, your exam is due tomorrow night at midnight. Those of you dealing with lab kit situations, there was a meeting I just came from, but I left halfway through, so hopefully I will be able to give you more information, if not this weekend, next week. Your exams, I will try to grade them within one business day. Keep in mind, tomorrow is not a considered business day, and also kind of actually have a lot going on tomorrow. So I graded as many exams as I can, but again, by Monday, about midday, you should start seeing the grades pop up. So yeah, check by about noon on Monday. I should have all the exams graded by then. Other than that, I will see you all next Monday. Thanks for those of you who could show up.